Thank you again for joining us today for our virtual meetup on enhancing Spark with H2O's AutoML using sparkling water. In this virtual meetup, we will learn how to use H2O's GridSearch and AutoML in sparkling water environment and how to put the trained models into production. My name is Saurabh Kumar, and I'm on the marketing team here at H2O.ai. I'd love to begin by introducing our speaker for the day, Nikhil Shekhar. Nikhil is a machine learning engineer at H2O.ai. He's currently working on our automatic machine learning platform, Driverless AI. He graduated from the University of Buffalo, majoring in artificial intelligence, and is interested in developing scalable machine learning algorithms. Before I hand it over to Nikhil, I'd like to go over the following housekeeping items. Number one, please feel free to send us your questions throughout the session via the questions tab in your console. We will be very happy to answer them towards the end of the session. This presentation is being recorded. A copy of the recording and a slide deck will be sent out shortly after the presentation is over. With that, the stage is yours, Nikhil.
Thanks, Saurabh. Good morning, everyone. So let's get started with one second. Yeah, with a brief intro about H2O. So for the folks who don't know about H2O, this is just a bit of information. So we started off in 2012, founded in Silicon Valley. We have our last round of funding was Series D, $147 million. We have multiple different investors from Goldman Sachs, Pingan, Wells Fargo, and quite a few more. We basically build AI products and machine learning libraries and enterprise solutions with these products. And we have a lot of customers. So we have around 20,000 companies using our open source H2O, and then we have 200K plus Meetup members. And we have a team size of about 240 right now. And we have offices in multiple different places across the globe. Our headquarters is based out of Mountain View. Then we have offices in New York, London, Paris, Ottawa, Chennai, Singapore, Prague. And so these are the few major products that we have at H2O, which includes the H2O open source, sparkling water, driverless AI, and H2O-Q. So we would be covering sparkling water, the AutoML from open source H2O, and some parts of driverless AI today to show how AutoML can be used in conjunction with sparkling water. So there are two solutions of AutoML from H2O. One is in the open source H2O AutoML. We'll see what are the and the other product is H2O Driverless AI. We'll see what are the difference between the AutoML solutions, which is from the open source, and the enterprise product that we have called Driverless AI shortly. And then we have a H2O model ops, and then we are coming up with an app marketplace, etc. So this is the basic pipeline which is being used to automate any data science workflow. So first we ingest the data, then we do some pre-processing, data exploration, then modeling, and then we deploy it. Then we manage our deployed models, then we keep monitoring it. And if there is a decay in performance, we go back and remodel it. And we have various kinds of users who use these ML models. So some of them are business analysts, some are data scientists, and then the DevOps engineer are primarily in charge of managing the models once they are built and deployed. And the products from H2O, like the H2O-Q, Driverless AI, ML Ops, H2O-3, and Sparkling Water, they all interoperate with each other to solve problems of various types. As in, H2O-Q would help you in building apps or vertical apps. Very soon, H2O Driverless AI is a pure AutoML solution wherein you just feed in your data set and then you get a model out of it. And H2O ML Ops would help you in monitoring the models, and H2O-3 and Sparkling Water patch in the gaps, as in H2O-3 helps you in building models on like really huge data on a cluster, and so does sparkling water. Sparkling water brings in the data munging capabilities to H2O3, and all these products interoperate with each other very well. We'll look into the details as we go along. So then now let's start with the H2O3 library first. So it's an open source machine learning platform. It has most of the leading algorithms which are used uh, in the industry. It can be accessed via R, Python, or H2O Flow. So H2O Flow is the UI based browser, something similar to Jupyter, if you would like to think about it in that way. And then the open source also has an automated machine learning library in it, which is called AutoML, and this can perform can build models on like on terabytes of data on a cluster of like a few hundred nodes, a few thousand nodes. And the models which you get out of H2O open source is in a Java jar, so which can be exported out of the machines running H2O3, and they can be used standalone anywhere on any underlying OS to score. So it's simple, and that helps with the deployment and makes it simple. And the score and the latency to score each row using this Java jar is pretty less. So it's really fast. And it's easy to provision and manage. Like you can spin up clusters pretty easily with one of our products, which is called Enterprise Team. So Enterprise Team it takes care of housekeeping and starting the H2O3 cluster and nodes, etc. So H2O open source is basically used for ML on big data. It's a distributed in-memory machine learning. It's fast and accurate. So if your code is running on like a single node machine, the same code can be used to build models on like a cluster of machines. So there is no need to write any additional code if you want to train your model on a cluster of a few hundred, a few thousand nodes. The code remains the same. And we have supervised as well as unsupervised ML algorithms, which can be accessed via Python and R, as well as the H2O flow, which is the browser-based UI. And then the artifact, the Java jar artifact, which you get out of after building the H2O models, is called a MOJO, which can be deployed anywhere. And this open source H2O also has an AutoML library, which is called H2O AutoML. We'll dig deeper into the AutoML library very soon. So yes, so the AutoML basically trains the best model in the least amount of time and saves a lot of user time. So once you have your data ready for your machine learning, to be fed into machine learning pipeline, so the AutoML will do some data pre-processing. These pre-processing are basically statistical pre-processing, as in like it will do imputation for you, one-hot encoding, standardization, etc. And then it will build different kinds of model. It will build random forest, GBM, stacked models, ensemble models, then GLM models, etc. And then at the end it shows you a leaderboard with the models having the highest accuracy on top, followed by the ones which have lower accuracy. And then usually we tend to see that the ensemble models, which are the ones which show up on top of the leaderboard, and they outperform the individual models. So the AutoML does the stacking, super learning, all by default. You just feed in that data set, choose your target variable and features, and then it does everything out of the box for you and gives you the final list of like a number of models which are really good to be used. But the data preprocessing does only statistical preprocessing and not exhaustive feature engineering. Let's go to H2O open source. I think we covered most of this. The only point I would like to make here is like H2O open source works on Hadoop, Spark, EC2, Kubernetes, and as well as on your laptop. You can just download it and then you just run the Java jar command, and then you can start using using the H2O3 library, or else you can even do a pip install and start using it via Python. So this is the architecture of H2O3. So there are multiple. So for instance, there is a cluster of 3 machines, and the H2O is running on EC2 in this case. So so H2O would be running on 3 nodes of an EC2, and then they can interoperate with each other. They talk to each other, and then the data set can be pulled on these 3 nodes via S3, and then it can be operated upon. So the H2O frame, on which the data operation happens, is are vectors. It's basically columns on which all the operations happen in memory, and then this can be accessed via Python or R, and it's all distributed data frames, collection of vectors which reside in memory, and all the operations happen in memory. And that's one of the primary reasons behind H2O3 being like super fast and super scalable. We have a lot of supervised and unsupervised machine learning algorithms in H2O3, namely the GBM, random forest, deep neural network, GLM, stack, ensemble, AutoML, etc. So it does normal imputation, normalization, one-hot encoding. So these are the things which are common to all algorithms which you use in H2O3, including AutoML. And at the end, you also get things like variable importance, model evaluation metrics, plots, etc. When you run the H2O3 algorithm, including the AutoML one. So this is the H2O open source architecture, as in it can, on the left side, they are basically data sources where the data can be read into. So once the data is read into H2O cluster, the data resides in memory. Then one can do an EDA, feature engineering, feature selection, and then use one of the algorithms which is available in H2O to do either supervised or unsupervised modeling. And then with the metrics which H2O spits out from the model, one can use those to plot different things. The plots are also come inbuilt when you're using H2O3, and so these plots along with the metrics can be used for model evaluation and selection. And then finally, you can use this model to predict, and this prediction can take in data from like other data sources, model storage, etc. And the models are exported as MOJOs, which are basically Java jars. And this can run on like on a cluster of Hadoop, Spark, Kubernetes, etc. And on the bottom of half of your screen, these are the major scoring environment where our customers use this exported Java MOJO. So the MOJO can be deployed in a Spark cluster, and then we can do parallel scoring. It can be deployed in Kafka if the incoming data is a stream data, and then it can be and then the MOJO can be doing super quick scoring on the streaming data. It can be used with Flink, NiFi, Hive, etc., and it can be accessed via R, Python, H2O Flow, and it can be accessed via like Java or Scala, and also some tools and other tools can be used to access H2O3 and run H2O3 models like Tableau, NIME, etc. So, and this is just a high level view of what all algorithms are available in H2O3. So if on the top there is the supervised learning algorithms, which are like GLMs, GAMs, DRF. So these are the ones which are usually popularly used in the industry. And then we have the models for framework for supervised model, which like stacked ensembles and automatic machine learning. So we'll concentrate on AutoML from here on. And then we have unsupervised learning algorithms like the k-means, PCA, GLRM, isolation forest, and aggregator, and a few miscellaneous for text analysis. Let's move on. So now, as I was saying, like why is H2O super fast? The one reason is everything, all the data resides in memory, and hence the computation is super quick. And then all the operations happen on vectors, and the way the vectors um, is manipulated or computed on is optimized via our custom Java data structures, and we do a lot of caching, compression, and CPU optimization, which helps in like the vertical scaling, and hence as a result of which the performance is really good, right from the data ingestion to the model training, model tuning, and then the spitting out of the model. So H2O3 helps you with scaling horizontally as well as vertically. And okay, maybe I can skip this because it's going more into more details of H2O cluster. I would like to jump to AutoML, sparkling water, and driverless AI, and how all these three can be used in conjunction. So this talks about the H2O MOJO, which is the Java artifact, and it can run on any underlying OS as long as it has Java installed on it. Now, yes, so this is a lifetime of the MOJO basically. So once you run your model on the H2O cluster, you get the MOJO file, and then this MOJO file can be deployed in different kind of environments, like the Java MOJO library can be deployed on JVM environment, and then we also have a C++ MOJO library which can be deployed in an environment where Java is not there, but C++ is available, and this can be accessed via Java, R, Python, .NET, etc., etc. So okay, now we are into the most important sections of our discussion today. Sparkling water. So sparkling water gives you basically a best breed of everything. It brings together Apache Spark and H2O3. So basically, one can use a Spark for data pre-processing and building the data pipelines, and then H2O3 to build models on a cluster which is fully distributed and parallelized. So H2O3 and sparkling water work together really well, and that's the USP of sparkling water. It basically helps in interoperability of Apache Spark and H2O3. So this is how a typical architecture of a cluster looks like. So a driver node has a Spark context as well as an H2O context, and the worker nodes also have this Spark Spark process running in it, and as well as an H2O process running on it. So these H2O and Spark process on the worker nodes interoperate with each other, and they are always in sync. As in, if you make a change in a data frame which is in the Spark process, it will be synced to the one with the H2O process, and all of this happens automatically. And then when we have both the H2O context and the Spark context, we can call methods either on the Spark context or the H2O context to compute or build a model interchangeably. And the sync between the H2O processes and the Spark processor happens internally. So all the data frames which are in the H2O process are always synced to the data frame which is in the Spark process. Yeah, so this is about Spark 2.0 API compatibility. So H2 algorithms can be used instead of the Spark ML or MLlib algorithms to build the models, because the H2 algorithms are way faster. It gives you a much higher control on the kind of models you want to build and things like that. And this gives you an idea of how sparkling water helps Spark and H2O3 to interoperate with each other. So once the data is being read from the data source, the data is passed as an H2O frame, and then this H2O frame can be interconverted to a Spark data frame and back to H2O frame in memory, and then data pipeline or the pre-processing or the data munging pipeline can be built. And once the data munging pipeline is built and we have the final set of features that we want to feed into the ML model, we can either use H2O3 algorithms or Spark algorithms. But we have seen that our customers or our users prefer using H2O3 algorithms because it's super fast, and the artifact which you get out of it is MOJO, which is like super quick to score on. So these are the few challenges in the AI model development. Like the feature engineering takes a lot of time of a data scientist to build models, and then the model building itself it can be pretty tricky. First in line would be which model should I be using? Should I be using GLM models or a tree model? And if tree model, should I be using a boosted tree model or a random forest and things like that? And then the once we have the model deployment is again challenging. Like how do we deploy the model? Yeah, if the way and usually the challenge in model deploying, like the scoring is slow. So H2O so if one is using H2O MOJOs, they are super quick, and they can be run on any underlying OS. So all those challenges are gotten rid of. So the H2O AutoML from the open source, it targets and solves the highlighted boxes. So basically it will do some statistical encoding, like the basic encoding, and then it will do the model building for you and the algorithm selection parameter tuning and builds model ensembles. And then it will give you a pipeline of the final model, which will be exported as a MOJO. Now, if you look on top of this, the value that driverless AI provide is what is being shown here. So driverless AI will do all of it out of the box, and one just needs to feed in the data set, select the target variable, select the feature columns, and then sit back and let driverless AI do all of this for you. So driverless AI does advanced feature engineering. It generates a lot of new features and uses them in the model if they are useful. And then it gives you an MLI module which helps you in explaining the model which was built, and then it gives you an autodoc which is a document format which documents all the details of the model which was built by driverless AI. So that's the difference between H2O AutoML and which is open source, and driverless AI. So this again gives the same picture. And now we'll go into some code and how do we actually do things. So this is the Spark pipeline API. So we leveraged that using sparkling water, as in you have the transformers which have the transform methods and converts data frame into another data frame. Like we can use transformers like tokenizer, bucketizers, element-wise products, etc. So we can, in the pipeline, we can chain multiple of these transformers and use them. So we use the estimator and then fit it, and then we get a transformer back. So the Spark pipeline will be used for data pre-processing, wherein we can chain multiple of these transformers to build the pre-processing or the data munging pipeline. And then sparkling water can be used to build any of the H2O3 models, which are available in H2O3, like the GLMs, gradient boosted tree, deep learning models, etc. And this is how we do it. So now this is the Python version or the PySparkling version of the code, but the code can also be written in Scala and R. So we import a few things, then we build an H2O GBM models, we pass in a few arguments, and then we create a statement which is a SQL transformer. So we are using a SQL transformer here, and then the H2O pipe, which you see the pipeline has two stages for simplicity right now. So one is the H2O GBM, and the other one is like the rename stage. But this pipeline can have like hundreds of stages, and one can do pre-processing to create the data pre-processing or data munging pipeline, and one of the stage can be building the H2O algorithm. And once we have this pipeline, we build the model by just calling fit on the on the on the train data frame, and then we can do a prediction using the model and then calling transform on it and passing it a validation or a test data frame. And so this can so this can help you in doing cross validation as well. So the cross validation happens with when you provide a grid of parameters and also and okay, so for cross validation, the original data is being split into the train and test, and the train data is being split into multiple folds. For instance, there's something like a k fold, and one of the k fold is being used as a validation data set in each and every iteration, and the other folds are used as a train. And this is how the cross validation happens inside of H2O, and then the test data set is kept separately, which is used at a later point of time after the model has been built to predict and check if there is a variance or a bias in the model. And then we go to grid search. So now we provide there are two ways of doing it. One is to provide the important parameters and to the grid layout, and then also ask H2O3 or the AutoML to do some random layout grid search. So this is so these are the libraries which can be used for the grid search. One is the cross validator, which does the Cartesian grid search plus cross validation, and then we have the train validation split, wherein the Cartesian grid search on which would be done only on the train and the validation split. And then in sparkling water, we can limit the execution time by max model or by runtime or by stopping criterion, which is not available in the cross validator or the grid search in Apache Spark. And it can also do a cross validation on train validation split ratio. So these are the few cross validation techniques which are not available in Spark but can be leveraged in sparkling water because it comes from the underlying H2O3, which the sparkling water would be leveraging. So this is how you provide the cross validation parameters, as in like the GBM parameters. So this is doing a cross validation on a GBM model. So you can provide a learn rate with a range of like, here it says like I multiplied by 0.01 for I in range 1 to 11. So we are basically providing a grid of parameters. So we are providing multiple values for learn rate, maximum depth, sample rate, column sample tree, and entries. So this JSON can be extended to include more parameters or reduce parameters. And then the grid search method which we are activating, which is H2O grid search, and then we are telling that okay, the algo to be used is H2O GBM, and we want to use N5-fold cross validation, and then the hyperparameters is the GBM parameters which we have defined above, and then we provide the labels and strategy and the max model that this grid search should be trying out, and what's the scoring function or basically an objective function. So we provide RMSE as the objective function, and then we call a fit on the data frame, and then we get these models from the AutoML. So this is like a leaderboard. So this has build multiple different models with different settings of the hyperparameters, and you get the last column is an RMSE. So based on which model you're comfortable with, you can pick one of these, or like maybe pick a few of these and blend it and do things like that. And now coming to the AutoML, so here we specify a base of a list of L-based models, and then we specify the meta-learning model, and then the AutoML takes over and builds model on top of it using the base models and the meta-learning model. So and this also just gave full cross-validation on all the models, and an out-of-fold predictions on one of the folds of the data set. And once it does the prediction, on the right side, if you see, it does the stacking, and then this stacking is being optimized by using a meta model to optimize the hyperparameters of the stack models. So that's where the meta model comes into the picture. And on the left side, the model building is like traditional ML model building with like k-fold cross validation, and the AutoML comes into the picture on the right side, where it makes use of the meta model to stack the outcomes of the models on the left side, basically the outcomes of the model 1, 2, and 3. Yeah, so it's so this explains the same thing with of how stacking works. So once we have the model, and if you want to do a predict on the new data set, so the model 1, 2, and 3 are being made use of. All of them give out their predictions, y1, y2, y3, and then they are fed into the meta model, which was already optimized in the previous step while we were training it, and then that meta model makes use of the predictions of the model of 1, 2, and 3 to give the final predictions. And then the models which were on the left side in the previous slide, so they can be like GLM1, GLM2, variants of GLM with different hyperparameters, GBM, etc. And then they are fed into the meta model, and then you get the final score. So usually what we see in that the individual models here, if you look at them, the AUCs are like 0.79, 0.75, 0.81, 0.84, and the AUC of the final stack model was 0.86. So whenever we do stacking, we see that there is an uplift in the accuracy, in this case the AUC. And this is how AutoML, it's very simple and straightforward to run H2O AutoML, and this is how it can be run. It's just like a one-line command which you need to use. So you import the H2O AutoML library, set the target column, and then if there are ignored columns, you can set that, and then you tell how many models it should be building. So we have set, in this case we have set it to 10, but this can be 100 and things like that, and then you do a fit, and then you get a leaderboard. So when you get the leaderboard, you get to see all the top 10 models which are built. If you, for instance, say if you have built 100 models, and if you do a get leaderboard, you will be able to see your best models on top, and the models which are not so good at below them. So this is how you can do target encoding in using sparkling water. And then yeah, so this is a better representative of the pipeline that can be developed using sparkling water and H2O AutoML. So there are two stages in this pipeline. So one is the target encoder, and the other one is the GBM model. So target encoder we could think of it as a pre-processing step, and then GBM as the modeling step. And as I was saying before, the stages can be many. It can be like 10, 20, or more. Basically depends on the kind of data pre-processing that you want to do before feeding the data into the ML model. And then we can just run it by using fit. That's the one which trains the model. And then if we want to to transform on the test data set, we can do using the transform data set. And then if we want to export this pipeline, so that's pretty straightforward as well. So you just call the pipeline model.save, and that would save the pipeline. And if you want to reload the same pipeline, you can just call pipeline model.load. So all these APIs are have been written by us, and it's up, and the intrinsic details of the APIs of what it does, how how the conversion between the Spark model or the Spark pipeline and the H2O model happens is all abstracted away from the user. And then the users have just pretty simple and straightforward APIs which they can use and leverage to build the pipeline as well as the model. Finally comes the deployment part. So if we want to load the pipeline in a Spark environment, we just need to create the Spark context, and then we do a initializer.load sparkling water jar Spark. So this basically adds sparkling water to all the Spark executors, and then the MOJO which we had extracted or we have saved the pipeline from the previous slide, we can load it, and now we have the MOJO in memory all over again, and it's live, and that can be used for scoring. So, and how do we use that MOJO which we loaded in the previous slide here for scoring? So we need a schema. So we define the schema of the data set, and then we read the schema by calling Spark read stream schema, and then we are passing in the schema, and then the original data set that we want to score. And now we use the MOJO one, which we created in the previous slide. We loaded it in memory, and we call that MOJO, and we do a transform on it, and we pass in the input data stream which we just read in the previous step. And now we have the output data stream, and this output data stream can be written to a streaming source, or we can just dump it into the file if the data being read is not, if the input data is not a streaming source of data. But this example caters to how you can read in streaming data, use the MOJO to score on the streaming data, and write the streaming data as an output on another stream. So that's what it was showing there. So till now we covered H2O AutoML and sparkling water, and how they can be used in conjunction to each other. And prior to that, we saw what are the capabilities that AutoML provides, and then we saw the difference between the open source AutoML and driverless AI. So the main difference was driverless AI does exhaustive feature engineering, but AutoML just does statistical feature engineering. So we will take like the next 5 to 7 minutes to learn a bit about driverless AI and how that interoperates with sparkling water, and then maybe we can take some questions. So driverless AI is a full-fledged AutoML product. It does, so here basically you don't have to do much, as in if you have a supervised learning problem, you just choose your target, feed in your data set, and then you get a model out of it. Then you have the MLI capabilities, to explain the model which was built. You'll get plots like Shapley values, line plots, PDPs, surrogate decision trees, and then you get the sensitivity analysis, etc. All of this out of the box, along with a document which documents the model, all the parameters, what pre-processing was done, what were the features that were created, and stuff like that. And this and driverless AI usually runs on a big fat machine, like as in it will sit on one machine which has GPUs. GPUs are not a necessity, but it speeds up the entire modeling by x-fold, and hence may make things very fast. So but driverless AI cannot run on the cluster. But we can use H2O-3, sparkling water, and driverless AI together to make to run things on big data, as in on the cluster of machines. How do we do that? We'll see that in the next few slides. Okay, so let me just go on 2 levels above. Driverless AI has a lot of automated features, feature engineering and machine learning capabilities. And then all these features are being used by the driverless AI engine. And once to build a model, once the model is being built, this model can be taken out, and then H2O and sparkling water can be used to retrain the pipeline which was built by driverless AI on big data. And then it can be deployed on a H2O and sparkling water cluster. So that's the idea behind making driverless AI model scale and run on clusters. So, okay, okay. So let's go through this real quick. An engineer, what the engineer would do is pull in the data from data sources. Here we are calling it the big data lake, and then the driverless AI would be leveraged to figure out the features that should be created on this data set. And the data set being pulled into driverless AI is like a subset of the big data, and that subset of data is being used to figure out what features should be generated and what model should be built. And once the model is built on this subset of data by driverless AI, that's exported as a MOJO. And then this MOJO is being used in Spark pipeline to uh, to do uh, the feature engineering, as in the pipeline can be used on Spark. The pipeline which came out of driverless AI can be used on Spark to create the new features which were figured out by driverless AI. And once we have these features created in the Spark environment, we can train using H2O-3 or any of the Spark ML algorithms to build the final model. So this final model is being fitted on the original huge data, and not the subset of data which was being pulled into driverless AI. So here driverless AI is leveraged to figure out what are the good features that needs to be created on this particular data set. And once we have that pipeline is taken out and then taken to the Spark environment or the sparkling water environment, wherein Spark is being used to do the data transformation. And then at the end of it, we build a model in H2O3. So that's the idea there. And how do we do it? We create a Spark session. We have the input data frame, and then the sample data frame is like a small sample of the input data frame. And then we export the output sample in the cell 38, which you see here. And this output sample is being fed into driverless AI, and this is how the driverless AI UI looks like. So you just tweak around with a few knobs, select your target column, and then let driverless AI do its stuff. And then the driverless AI builds the model, and this is one of the models from an experiment on a data set called credit card, which is basically to predict which is a binary classification problem to predict whether the customer will default or not in the next month. This data set is from UCI library. So this is how the MOJO or the driverless AI model looks like. So on the left side, they are all like the columns like limit, balance, age, pay zero. See, so these are the features from the input data set, and then in the middle column, we see the features that were created on these input features by driverless AI, and all of these were fed to an XGBoost GBM model, and then the predictions were made, right? So, so this estimator, like this pipeline is being read, which was built by driverless AI on a subset of data. This can be read into sparkling water using the cell 4, which you see here. So here what we are doing is we are calling H2O MOJO pipeline dot create from MOJO. So that's the one which is reading the model which was built by driverless AI. So now we have the MOJO transformer, and then we'll apply this MOJO transformer here. Okay, let's go to the next GBM estimator, which is there, right? So here we are building a H2O GBM model, and then the feature, if you look at the feature columns, that's where the MOJO transformer is being used to get the output columns and get the feature columns. And then this pipeline has two stages: the MOJO transformer and the GBM estimator. So the MOJO transformer will transform um, the data set which will be fed into this pipeline, and this data set can be like terabytes of data. So the model we got out of driverless AI is being read in sparkling water, and it's being fitted on terabytes of data. So we are basically creating the new features, which is like the second column, which we see like the frequent transformer on multiple different columns. So we are creating all those features on the terabyte of data, which is the big data in sparkling water environment. But these features were figured out by driverless AI on a subset of data set. And then we create a pipeline which has two stages here now, which is the first is the MOJO transformer, which does the transformation of the features, and then the final model, which is an H2O GBM model, which we are building here. And now we to fit the pipeline, we need a train DF. So we are creating a train DF here. This is just a standard Spark code. So we create a train DF, and then we do a pipeline.fit. So the pipeline here is the one that we created in the previous slide. So which has two stages: the MOJO transformer and the GBM estimator. Then we have the final model, which can be used to like now transform, predict, and things like that. So if in the cell 18, if you look here, the transform, we ran a transform, and then we selected one of the columns. So this column, the 39 underscore cluster distance 6 colon p underscore 06, this is one of the features which was built by driverless AI, and now we have successfully transformed our big data in a sparkling water environment to have these features, and then we train an H2O GBM model on top of it. So there are a few limitations on this, like as in the transform. We have lots of transformer in driverless AI, but not all of them are big data friendly. And then there's some API improvement which needs to be done, and that the auto documentation which comes out of this, that needs some introspection or some API changes and etc. So that's all from me. So if you guys have any questions, I would be happy to take them.
Wonderful. Thank you so much, Nikhil. We have a few questions. Let's begin. How can we implement my current machine learning models running in Python onto the Spark or H2O.ai platform?
Yeah, so okay, so the original models are in Python, right? And they need to be transported into Spark and H2O.ai. Yeah, okay. So it's pretty straightforward. Like you would be building a pipeline, like the data pre-processing pipeline in Python, and then building a model at the end of it. So you can use H2O or the sparkling water APIs to build the same data pre-processing pipeline, and then build a model at the end of it. So that's like the programmatical way of doing it. But if you use driverless AI, you just feed in your data set, it will do all of the pre-processing, the feature engineering, etc., everything for you, and give you the final model. So one is the API wherein you'll have to go and code and stuff, and then build the pipeline, and then build the final model. So there's no automatic conversion between automatic way to convert your Spark pipeline, convert your Python pipeline and model into sparkling water environment or the H2O platform. So it would need some hand coding if you're using the open source APIs. But if you're using driverless AI, it can just be like feed in the data and you get results out of it.
Thank you. How can I automate the entire stack from data gathering to production and everything in between? and keep on iterating and improving the models in an automated fashion. Would you like to begin?
Yes, sure. So H2O as a company, we don't do any data gathering or data pre-processing, but there are multiple ETL tools which can be leveraged to do the data gathering, data pre-processing. And once the data is in some standard form, H2O platform can be made use of to do data like to do feature engineering, modeling, optimization of the model, and then deploying it. So we have an H2O model ops now, which can help you in managing your model over a period of time. Whether the model decays, then you can retrain it and things like that. But the data gathering and some cleansing of the data needs to happen before the data comes into the H2O AI platform. I hope that answers the question.
Thank you. What is the difference between PMML versus MOJO, and is there a way to export?
Yes. So PMML is the standard way that Spark exports its model, and we have seen that PMML models are pretty slow compared to the MOJOs that's available for H2O models. So H2O models basically, like if you are running a MOJO on one machine, it can score like 4,000 rows in a second, and that you can run that on multiple machines in parallel. So there is no limit on how many rows you can scale like per second. You can, if you are scoring 4,000 rows on one machine per second, and if you have like 10 machines just doing scoring, so you can score like 4,000 into 10 or 4,000 into X basically. But loading the PMML is pretty slow, and scoring is slower. So you cannot really use it for like streaming scoring in many scenarios if your pipeline and your model is complicated. And there is no direct way to convert PMML models into MOJOs, but there is something new which is coming up called MLeap. So Java MOJOs, this is still work in progress. So Java MOJOs and the PMML can both leverage MLeap to talk to each other, but the support is still not there for all the models yet.
Thank you.
So those were the pros and cons of PMML and MOJOs.
Great. Somebody's asking for a sample notebook for reference on the H2O open source platform.
So I think we can share that out along with the presentation, Saurabh. Yeah.
Right, and that also answers a few questions on slides and recordings. We'll share them after the presentation gets over. Somebody's asking, could you explain how the model explanation works?
Yes. So there are in driverless AI, we have some pretty standard techniques to explain the models, as in if you are aware of the Shapley values or the Shapley plots, the line values, the line plots, the partial dependency plots, and then decision tree surrogate models or sensitivity analysis or GAMs. So these are like straightforward. These are like standard techniques which are used to explain black box models which are like pretty complicated, as in if you have a stacked model, right, you cannot it's not easy to explain. But if you have a GLM model, it's pretty straightforward. You just look at the weights and you can explain your predictions. But if you have like an ensemble of 20 models, there is no straightforward way of explaining it. So we use these proxy techniques to explain the model, which is like pretty complicated. But and these proxy techniques are the ones that I just mentioned before. And if you want to know more about each of these techniques, you can go to our documentation page, like docs.h2o.ai, and then go to driverless AI, and then go to the machine learning interpretability section, and you'll get all the details there. Also, if you search for MLI, what's the book title, Saurabh, the one from Patrick Hall and Navdeep, which explains all the techniques on MLI?
Absolutely. So the last version was called an Introduction to Machine Learning Interpretability. The latest one that was just released last week by O'Reilly is called Responsible Machine Learning, and they are all available on our website under the resources section.
Yes, so these books would be like the best places to understand each of these machine learning libraries in depth, and they are available. So the book is published by O'Reilly and by data scientists at H2O in conjunction with each other, and it's free for download from our website. So you can just go there, download it, and go through it.
Great, thank you, Nikhil. Next question. Does H2O support iterative learning using pre-trained H2O models on new data instead of training on complete data again?
Yes. So in driverless AI, once you build a model, you can always add the incremental model as and when you are gathering the data, and then just train on the new data set. So it makes use of the previous model which you built, and then optimizes the hyperparameters to take care of the new data set which you added in. So that's like the usual machine learning process. Like you build a model today, and then you have a good model today, and in the next 6 months you collect more data, and you want these 6 months data to be fed back into the model, and the model to be fine-tuned again. So after 6 months you can do a mini training which would fine-tune your model, taking care of the incremental data which you fed in, which is for the maybe the next 6 months. So yes, we do take care of it, and we have that provision.
Great. Our last question. Does driverless AI also work with text and image data?
Yes. So we have had the support for text data for like over a year now. We added support for image data like 3-4 months back, and driverless AI can handle NLP use cases and image use cases as well. And in NLP world, we are pretty advanced. Like the NLP framework of driverless AI also makes use of BERT models, the various variants of BERT model like FinBERT if the data set is from financial domain, or like the mini BERT, etc. And we make use of a lot of pre-trained models as well as like the standard techniques of using word to CNN transformers, DF, etc. And in the image world, we also make use of a lot of pre-trained image networks like the ImageNet, ResNet, etc. And there is capability or functionality wherein you can bring in your own pre-trained networks for both NLP and images inside of driverless AI and make use of them as well. And again, for more details on what all functionalities are supported, you feel free to visit docs.h2o.ai, and in there go to the driverless AI section, and then you can search for images and NLP, and you'll get all the details listed out there.
Great. Thank you so much, Nikhil, for taking the time and doing a great presentation and answering our questions.